Hello students, in this session
Let us solve a question on bending stresses. A cantilever beam has a square cross-section of 10 mm by 10 mm. It carries a transverse load of 10 kN. Considering only the bottom fiber of the beam, the correct representation of the longitudinal variation of the bending stress is. This we have to select out of 4 options. So here we are given beam with a cantilever beam. Cantilever beam is there, which has 2 meter length, and a 10 kilonewton load is applied at the center of the cantilever beam. The cross section area is given 10 millimeter by 10 millimeter. We have to consider only the bottom fiber, this fiber only, bottom fiber of this cantilever beam, and we have to draw the bending stress at the bottom fiber, right, which is the correct option of the out of these four, correct option for the bending stress distribution at the entire length, right. This we have to find out. So this question was asked in gate 2005. So let us solve this question.
this question contains a cantilever beam with a point load at the center. The total length of the beam is 2 meters and it has a square cross section area 10 millimeter by 10 millimeter. We have to draw the bending stress diagram of this beam, and for the entire length the stress to be taken at the outer fiber, which is the lower part of the beam, at the lower part at the outer fiber. Let us solve this question. We know that the bending stress distribution for a beam is generally linear. You know, it is linear, not generally. For uniform cross section it is always linear. So it is linear like this. It is maximum at the outer fiber, and zero at the neutral layer, right? This is the maximum stress. This is the maximum bending stress, right, at the outer fiber. So once the outer fiber is fixed, so we have to find out here that at y max, so we will get sigma max, right? So we know bending equation that is m by I sigma by y E by r. So stress will be equal to my by I, my by I. This is the bending stress with respect to y, right? And if y is fixed, then we have to find out the maximum bending stress that will be the maximum bending stress at a distance y max, that is outer fiber, right? It is to be find out at outer fiber. Now y is fixed for the entire beam because we have to find out the outer fiber, lower outer fiber for the entire beam. So y max is fixed, I is constant, moment of inertia is constant. Then sigma max will be a function of only bending moment. So basically we have to draw the bending moment diagram, and from that we can find out the bending stress diagram, right? So what will be the bending moment for the beam? I am making it a linear beam like this so that it is easy to see here. I am making this beam like this, right? This is 10 Newton. That is not a difference. A, B and C, right? And now we have to draw the bending moment diagram, and from that bending moment diagram, bending stress diagram can be drawn, right? So bending moment diagram we have to draw, right? So here there is no force is there. So if there is no force, the bending stress will be 0. So bending moment will be 0. So from B to C, there is no need to take the section, right? If I take the section here, there is no moment is there, so no force is there, so there is no moment. So bending moment will be a 0 from B to C because there is no force here, right? I can take the section here only, and taking the section here from the free end. So let us take the section from the free end at a x distance from the free end, right? So what will be the bending moment? Mx, right? We know from C to B there is no force is there, so no bending moment will be there. So we have taken this as 0 bending moment from B to C. Then Mx from which is valid from C to B, which is valid for C to A, and that will be equal to force multiplied by the x, right? So x we are taking from the free end. If we are taking from the free end, that should be equal to 10 multiplied by x minus 1. So this is 10 multiplied by x minus 1, and that will be negative, because from according to our sign convention it is a negative force on the right side, right? Negative. So 10 multiplied by x minus 1. So this is the linear variation, negative direction, right? And MC, where x will be 1 meter, this will be 0, and MA, where x will be 2 meters, this will be minus 10 Newton meter, right? So it is a linear variation from 0 to minus 10, linear variation because x is there, right? From 0 to minus 10, suppose this is minus 10, and this is the variation like this, right? So from here, this variation is linear variation like this, right? So this is the bending moment diagram, and it is negative, right? So here it is minus 10, so this is minus 10 Newton meter, so this is minus 10, right? Basically minus 10 Newton meter up to this point, right? And this is A, C, B, and from C to B it is 0. So this is the bending moment diagram of, this is the bending moment diagram, right? And we have to draw the bending stress diagram, how to draw the bending stress. So if it is linear, then bending stress will be linear, but we have to check what is the value. So we can find out the value as, this is minus 10 Newton meter, minus, I am skipping, it is shown that minus here 10 Newton meter, this point is 10 Newton meter. So we can take only 10 Newton meter because it is proportional to this, right? So, and linear variation will be there, so stress will be also be having a linear variation. If I draw here bending stress distribution, if I draw here, it will also be a linear variation like this, similar to bending stress, but magnitude will be different like this, right? So bending stress will also be the linear variation like this, right? It will be linear variation from A to C to B. So it will be linear variation, right? And compressive stresses will be there. But what will be the magnitude? This value, right? So that we can find out at 10 Newton meter what is the compressive stress, maximum compressive stress. That will come out to me from here, right? We know that sigma max is given by my by I. M, what is M? M is 10 Newton meter multiplied by y. Y is this distance, which is half of the 10, that is 5 millimeter. So 5 millimeter divided by I is BD cube by 12, right? I we know that is BD cube by 12 for cross section. So we can write here B. What is B? That is 10, and D is also 10. So 10 multiplied by 10 cube by 12, right? So this is the maximum stress. Solve it and you will get what value you will get, that is to be 10 to 10 cancel, this is 60. Actually this should be kilonewton because there is some mistake in this question. It should be kilonewton, so that proper answer can be obtained, right? This is kilonewton, it should be kilonewton meter, then only we will get the 60 megapascal answer here, which is given in the option. So 10 kilonewton meter, it means 10 multiplied by 1000 and then 5, right? So now 10 to cancel, 10 cancel, you will get 60 megapascal. So answer will get 60 megapascal, right? It means this value is basically 60 megapascal, right? 60 megapascal. So this is the answer of this question, that the 60 megapascal stress is there, which is maximum stress, sigma max, and it is compressive, and it is 60 megapascal, and it is linearly varying because it is proportional to bending moment. If bending moment is linearly varying, it will be linearly varying, and at C point it is 0, and from C to B compressive stresses will be 0 because there is no bending moment. If M is 0, sigma will be 0, right? So that's why the maximum stress is, sigma max is 60 megapascal. and the variation will be a linear variation from 60 to 0 from A to C, and then from C to B, 0 when stresses. So this is the variation. So you can see here, and you will see this is a option A. So this is the answer, and this is option A. Option A.